Hello everybody. Today we will have third session on synchronous generators. I am Dr. Nagesh Prabhu, Professor and Head, Department of E&D, NMAM Institute of Technology, NITE. In the last session, we had discussed relationship between speed, poles and frequency. We had also covered armature winding coils, full pitch coils, short pitch coils, difference between concentrated coils and distributed coils. The advantages of short pitch and distributed windings have been discussed in the last session. The main advantage of short pitch and distributed winding is that it saves copper and it reduces the harmonics in the induced EMF. We have also derived the derivation of EMF equation in the last session. In today's session, we will quickly review on representation of single turn and multi-turn coils. We will also look at how we can visualize the coil span and pitch factor. We will also review quickly on concentrated coils and distributed coils. We will solve many numerical examples. Video of working of hydroelectric power plant followed by conclusions. When we look at the difference between single turn and multi turn coils, see here we have a single turn coil. So, that means the coil side 1 is placed in first slot and the other coil side placed in the other slot, and it has only one turn. You can see this here, and it is denoted as single turn coil, and this is the representation of a single turn coil, and the distance between the two coil sides in terms of armature slots is called as coil span, and it is denoted here. So, now when it comes to multi-turn coil, we have many turns in one coil side. So, this is coil side, this is also another coil side. So, we have denoted it as coil side 1 and coil side 2. So, we have more turns in multi-turn coil. So, as it is seen here, so this is the first turn followed by second turn, and for simplicity only 2 turns have been shown in multi-turn coil here, but in actual practice there can be large number of turns in a multi-turn coil, and we can represent multi-turn coil as shown in this figure. So, now usually if the coils are full pitched, then these two coil sides should have a phase difference of 180 degree. So, that means the coil side exactly under the midpoint of north pole should be connected to the coil side which is exactly under the midpoint of south pole. So, that means the distance in terms of armature slots between these two coil sides will be 180 degree electrical. So, if we visualize the coil span and pitch factor Kp, so this figure is going to help us. If the coil span is equal to pole pitch, as just I have discussed, one of the coil side of a coil is placed under the midpoint of north pole, under the slot which is directly under the center of a north pole. The other coil side is placed in a slot which is directly under the midpoint of a south pole. So, this is the coil span corresponding to pole pitch, which is equal to 180 degree, and alpha is the short pitch angle, which is 0 here because the coil pitch is equal to pole pitch. So, pitch factor which is given by cos of alpha by 2. By substituting alpha is equal to 0, so we will get cos 0 which is equal to 1. And in the case of short pitch coils, coil span is the distance between two sides of the coil in terms of armature slots is less than pole pitch. You can see here this is full pitch and the pitch of the coil is less than the pole pitch. So, in such a case alpha is greater than 0 and Kp is always less than 1. So, now When we look at the concentrated coils and distributed coils, so now in concentrated coils we have all the turns. Say in a particular coil, if the coil has 30 turns, which is again a multi-turn coil, and in one coil there are two coil sides, and all the conductors or all the turns of one coil side is placed in single slot. Naturally, the depth of slot that is required for concentrated coils is large. Suppose in the case of distributed coils, where the distributed coil has its own advantage in terms of reduction in harmonics and better EMF waveform, so we prefer to go for distributed coils. And in the case of distributed coils, the total turns in one coil group, see there are 3 coils in a coil group, and these 3 coils together in the coil group, which is allotted for say one particular phase, and this coil group together should have say 30 turns, which is something equivalent to concentrated coils. That means the 30 turns in each coil side of a concentrated coil is now distributed amongst 3 coil sides of the coil group in a distributed coil. So that means the number of turns which are placed in each of the coil of a coil group in this distributed coil is given by T by M, where M is the number of coils in a coil group. So each coil in a coil group will have only 10 turns in this particular case, and in order to accommodate these 10 turns in the slot, you can compare the depth of slot here and depth of slot here. So with the distributed coils, the depth of slot is greatly reduced, and reduction in depth of slot is reducing the leakage reactance effects and reduces the reluctance of the magnetic path, and hence lesser MMF is just good enough in order to maintain the air gap flux, and also the regulation of the alternator is better with the reduction in the depth of slot, because the leakage reactance effect is reduced. So now let us consider, as discussed earlier, 3 coils in a coil group, and the MMF distribution of 3 coils when considered separately is given in B, C, D. So now the group of these coils are connected in series together, and MMF distribution the resulted because of the connection of 3 coils in series in a coil group is the stepped waveform. So now you can notice this stepped waveform, what is shown here, this is the resultant MMF because of the distribution of coils, and you can see this approaches, the waveform approaches more or less sinusoidal, and air gap flux density is very near to sinusoidal, and we know that if the air gap flux density approaches sinusoidal, the induced EMF will also have a sinusoidal variation with the lesser and lesser harmonics. So if you distribute the winding into more number of slots, then we will have sinusoidal distribution, almost we will get sinusoidal distribution, and hence the distributed coils will reduce the harmonic content in the induced EMF. So near sinusoidal MMF waveform is resulted, and it reduces harmonics in the induced EMF. This is the effect of distributing the coil, and if the harmonic is reduced, the losses are reduced, and since the losses are reduced, it increases the efficiency of the machine which is connected to this alternator. So now let us consider numerical example. So we will have a 8 pole 750 RPM 3 phase star connected. Star connected means we have 3 windings, similar ends of 3 windings are connected together to form a star point. So in turn we will have 4 terminals what is coming out of the alternator, R, Y, B and N stands for neutral, where similar ends of 3 windings are connected. So, that is what is meant by star connection. And this alternator has 72 slots, each of which having 10 conductors. So, that means in each slot we have 10 conductors. We need to calculate the RMS value of the EMF per phase if the flux per pole is 0.1 Webers and the winding factor is given by 0.96. So, let us solve this numerical. So, winding factor Kw is nothing but Kp into Kd, which is equal to 0.96, which is already given. The other data what is given is P is equal to, that is number of poles, is equal to 8, speed is equal to N, in RPM it is given as 750. So, we can calculate the frequency of the induced EMF when we know poles and speed. So, it is given by P into N divided by 120. Substituting into this the values here. So, we will get 8 into 750 divided by 120, which is equal to 50 hertz. Total number of conductors are armature conductors, are denoted as Z here, which is equal to number of slots. So, total number of slots round the periphery of the armature into conductors per slot. So, it is given in the numerical that conductors per slot is 10 and we have 72 slots altogether in the inner periphery of the stator. So, we will have total 72 into 10, which is equal to 720 conductors. So, now this 720 conductors are all together in total in the inner periphery of the stator. All these 720 conductors are housed in 72 slots. So, since the winding is designed for 3 phase, so we will have for each phase 720 divided by 3. So, we will have conductors per phase, which is denoted as ZPH or Z phase, which is equal to 720 divided by 3, we will get 240 turns per phase. So, that means we know that here 2 conductors constitute 1 turn. So, turns per phase is naturally given by Z phase divided by 2, because 2 conductors constitute 1 turn. So, Z phase divided by 2 will give us turns per phase and it is given as 120. So, therefore, we know the equation for the EMF per phase, which is given by 4.44 kW. Kw is Kp into Kd. F is the frequency of the induced EMF, and phi is the flux per pole in Webers. T phase is the turns per phase. So, if we substitute 4.44 into Kw, which is already given 0.96, into 50, that is frequency, into phi, that is flux 0.10, turns per phase as we have calculated in the last step, that is 120. Altogether, if you multiply, we will get 2557.44 volts. So, now this is the RMS value of the phase voltage. We need to calculate the line voltage EL. So, line voltage and phase voltages are related in this fashion, because in the case of star connected winding, we have line voltage is equal to √3 times the phase voltage, and when we multiply line voltage, when we multiply phase voltage by √3, we will get line voltage as 4429.616 volts. Let us consider solving one more numerical. A 8 pole 3 phase 50 hertz star connected AC generator. AC generator is nothing but alternator. Sometimes it is also denoted as synchronous generator, and it has 24 stator slots. Find the number of conductors per slot if the flux per pole is 60 milliweber and the terminal voltage is 1100 volts. Whenever such kind of data is given, that is terminal voltage is specified, we need to know terminal voltage is nothing but the line voltage of the alternator. Terminal voltage is the voltage between two line terminals of the alternator, and usually the alternator is rated with the terminal voltage and terminal voltage is the line voltage. So, keeping this in mind, we should be able to solve the numerical, and it is also given that assume full pitch coils. For full pitch coils, pitch factor is a 1. Now, the given data, number of poles are given as 8, frequency is given as 50, S is number of slots altogether 24. Now, we can calculate speed, because frequency is given, we can calculate speed as 120 F by P, which is equal to 120 into 50 into 8, which is equal to divided by 8, which is equal to 750 rpm. Now, let us calculate number of slots per pole, and slots are 24, poles are 8. So, we will get number of slots per pole, which is equal to 3. Now, we need to calculate slot angle beta, and beta is given by 180 degree divided by 3. 180 means number of electrical degrees, or 180 degree electrical for one pole. So, in under one pole there are 3 slots. So, 180 degree divided by 3 will give us 60 degree electrical. That means, each slot will have a measure of 60 degree electrical, that is what is called as a slot angle. And this M is given as slots per pole per phase. So, that means, if 3 slots are allotted under each pole should also have 3 windings allotted for 3 phases. So, it is a 3 phase machine. So, number of slots per pole under each phase is given by 24 divided by 8 into 3, which is given as 1. So, that means, under 3 slots, this poles, one pole means 3 slots. These 3 slots are allotted for 1 slot for each phase. That means, 1 slot is allotted for R phase, 1 slot is allotted for Y, 1 slot is allotted for B phase. So, we will have M is equal to 1, where M is given by slots per pole per phase. Now, we are ready to calculate distribution factor. Distribution factor Kd is given as sin m beta by 2 divided by m into sin beta by 2, and we know that m is equal to 1, beta is the slot angle which is equal to 60, and beta is again 60, which is substituted here, m is equal to 1. So, we will get a distribution factor which is equal to 1. It should be noted that if slots per pole per phase is equal to 1, we always get a distribution factor which is equal to unity. So, that means, it is as good as we have not distributed amongst various slots under each phase. So, because one slot is only allotted for one phase under a pole. So, it is given that the coils are full pitched. So, for full pitched coils Kp is given as 1. So, now flux is also given as phi, which is equal to 0.06 Webers, and terminal voltage is given. So, as I have mentioned earlier, the moment when terminal voltage is given, we should understand it is the line voltage. So, phase voltage need to be calculated. So, phase voltage is given by 1100 divided by square root of 3, which is equal to 635.085 volts. So, now we can calculate total number of conductors Z. Now, by applying into the equation for E phase is the induced EMF per phase, which is equal to 4.44 Kp Kd. We have already calculated Kp as 1, Kd as 1, frequency as 50, phi is given. So, E phase we have calculated here 635.085. So, we can calculate a T phase. So, now the T phase what is so calculated is coming to 47.68. So, this fraction does not exist because number of turns cannot be a fraction. So, we can round it off to 48. So, turns per phase is rounded off to 48 to a whole number, because fraction number as far as number of turns is not practicable or not practiced. It is not possible to have fractional for a fractional point for number of turns. So, we round it off to 48. So, now conductors per phase is given by Z phase, which is equal to 48 into 2. So, because each turn constitute 2 conductor, there are 48 turns, wherein we get Z phase which is equal to 48 into 2, which is equal to 96. So, now Z is the total number of conductors for this stator, which is given as conductors per phase into number of phases. So, we will get 96 as obtained in the previous stage into 3, which is equal to 288. So, now conductors per slot. So, that means we have total conductors as 288 and we have 24 slots. So, each slot will have 12 conductors, and we have calculated and arrived at the solution that we have been asked for. Conductors per slot is equal to 12. Let us consider one more numerical. A 4-pole 3-phase 50 hertz star connected AC generator has 24 slots. Find the number of conductors per slot if the flux per pole is 61.7 milliweber. The terminal voltage is 1100 volts. Assume full pitch coils. So, this step is similar. Number of poles is given as 4, F is equal to 50, S is equal to 24. So, we have now N is equal to 1500 and N is slots per pole, which is given as 24 and poles are 4. In the earlier example poles were 8 and in this present example poles are 4. So, we will get slots per pole as 6. Now, slot angle can be calculated as 180 is degree electrical for one pole, and under one pole there are 6 slots. So, we will get 30 degree electrical as a slot angle. Now, M can be calculated as slots per pole per phase, which is equal to 24 divided by 4 into 3, we will get 2. So, M is slots per pole per phase is calculated as 2. So, now distribution factor can be calculated as sin M is 2, beta is 30, then here again M is 2, beta is 30. When we substitute and solve for, we will get 0.9659. So, Kp is equal to 1 because it is assumed that the coils are full pitched. Flux is given already, terminal voltage is 1100 and we calculate E phase just like earlier case, and E phase is 635.085. Total number of conductors to be determined. When we substitute for E phase and Kp is equal to 1, Kd as calculated as 0.9659, F is 50, phi, and we can calculate T phase as 48.002. So, it can round it off to 48, and conductors per phase is nothing but 48 into 2 96, and total conductors per slot can be calculated as 96 into 3 divided by 24 is equal to 12. So, let us consider the next numerical. A 8 pole 750 rpm 3 phase star connected alternator has 72 slots, each of which is having 10 conductors. Calculate the RMS value of the EMF per phase and line voltage. The flux per pole is 0.1 Weber. The coils are short pitched by one slot and the windings are distributed. P is equal to 8, that is given. Speed is equal to 750. So, frequency can be calculated as P n by 120. So, P into n divided by 120, which is equal to 50 hertz. Total number of conductors is given by number of slots into conductors per slot, and it is calculated as 72 into 10 is equal to 720. Conductors per phase, since there are 3 phases, ZPH is equal to 720 divided by 3, which is equal to 240. Turns per phase is equal to Z phase divided by 2, which is equal to 240 by 2, given as 120. Now, slots per pole. So, we have in total 72 slots, we have 8 poles and slots per pole is 9. Now, slot angle can be calculated as beta, which is equal to 180 divided by 9, which is equal to 20 degree electrical. Slots per pole per phase is calculated as 72 divided by 8 into 3, which is equal to 3. So, that means now 3 slots are allotted for R phase, 3 slots are allotted for Y phase, 3 slots are allotted for B phase in any one pole. So, under one pole there are 9 slots, or we can say 9 slots are under the influence of one pole, next 9 slots are under the influence of next pole. So, under each pole, that means we have 9 slots, and these 9 slots are allotted for each phase equally. So, R phase will have 3, Y phase will have 3, B phase will have 3 slots. So, slots per pole per phase is calculated as 3. Now, it is given that coils are short pitched by one slot. So, that is what is mentioned in the numerical. So, if the coils are short pitched as one slot, short pitch angle alpha is equal to beta. Beta is equal to 20 degree. That means one slot measures 20 degree electrical. Short pitch angle is equal to alpha, and coils are short pitched by one slot. So, that means alpha is equal to beta, which is equal to 20 degree. So, Kp can be calculated as cos of alpha by 2, which is equal to alpha is equal to 20. So, we can substitute this 20 here. So, 20 by 2 comes to 10, cos of 10 is given as 0.9848. We can calculate distribution factor Kd, which is given as sin m beta by 2 divided by m sin beta by 2. So, now in this particular example, m is equal to 3, beta is the slot angle, which is 20, and when we substitute m and beta, we will get 0.9598 as a Kd. Winding factor can be calculated as pitch factor into distribution factor, that is Kp into Kd, which is equal to 0.9848 into 0.9598, which is equal to 0.9452. Therefore, E phase, that is a phase voltage, the RMS value is given by 4.44 kW, that is winding factor. So, sometimes we can directly substitute, instead of calculating winding factor, we can substitute 4.44 Kp Kd directly here. So, in case you should know what is Kw, so that is why it is shown separately here. So, Kw, which is equal to Kp into Kd, so that is given as 0.9452. So, that I have substituted here, into frequency 50, flux 0.10, turns per phase as calculated in the earlier step 120. So, phase voltage RMS value is given as 2518.0128 volts, and since it is a star connected alternator, line voltage is equal to EL, which is equal to root 3 times the phase voltage, and by substituting this here we get 4361.326 volts. Let us consider the next example. In this example, we have a 3 phase 16 pole alternator which is star connected, and it has 144 slots and 10 conductors per slot. The flux per pole is 0.03 Weber and the speed is 375 rpm. Find the frequency, the phase EMF and line EMF. The coils are short corded by 2 slots. So, this is the change. So, we need to know the coils are short corded by 2 slots. The meaning of this is coils are short pitched by 2 slots. So, as usual we can start with calculating frequency. Number of poles 16, speed is 375, we will get frequency as 50 hertz. N is equal to slots per pole. So, we will have 144 slots under 16 poles. So, slots under each pole are 9. So, slot angle we can calculate as 180 divided by 9, which is equal to 20. M is slots per pole per phase, is calculated as 144 divided by 16 into 3, which is equal to 3. Short pitch angle alpha is equal to 2 times beta, that is because the short pitch angle is 2 times beta. Beta is the slot angle, and it is given that coils are short corded by 2 slots. So, 2 times the slot angle is given as alpha. Alpha is equal to 2 into 20, which is equal to 40 degrees. So, now pitch factor is equal to cos of alpha by 2, which is equal to cos of 40 by 2, which is equal to cos 20, which is calculated as 0.9397. Distribution factor can be calculated as m is equal to 3, beta is equal to 20, and when we substitute accordingly we will get 0.9598. So, total number of conductors in the stator is given by Z, which is equal to 144. 144 is total number of slots into conductors per slot, that is 10, and it amounts to 1440. So, now conductors per phase, Z phase is calculated as 1440 divided by 3 as 480. T phase is equal to Z phase by 2, which is equal to 240. So, we can calculate E phase, that is RMS voltage of one phase or across any phase, is given as 4.44 Kp as calculated earlier, Kd into F frequency 50, flux per pole is 0.03, T phase is 240. So, we will calculate it as 1441.635. The line voltage is root 3 times E phase because it is star connected, and root 3 times 1441.635 is calculated as 2496.985 volts. Consider next numerical. A 3-phase star connected alternator with 12 poles generates 1100 volts on open circuit. Open circuit means alternator is not loaded, the terminals of the alternator are kept open and alternator is not connected to any of the load, and it runs at a speed of 500 rpm. Assume 180 turns per phase, a distribution factor of 0.9598, and coils are short pitched by one slot. So, that means this data can be used to calculate Kp, that is pitch factor. Distribution factor is already given as 0.9598. Find useful flux per pole, frequency, winding factor, and estimate the number of stator slots and conductors per slot if slots per pole per phase is 3. So, here m is given and we have been asked to calculate all these things, that is number of stator slots, winding factor, frequency and useful flux per pole. So, let us start with calculating frequency. Pn by 120, P is number of poles which is 12, N is 500, 120. So, we will get 50 hertz. Distribution factor, the value is given as 0.9598, but we know that distribution factor is given by sin m beta by 2 divided by m sin beta by 2. So, slots per pole per phase is given in the numerical. So, it is given as 3. So, when we substitute for m and the only unknown that is left out is beta. So, we can solve this equation for beta because we know the value of Kd, and while solving we get slot angle beta as a 20 degree electrical. So, n is equal to slots per pole, we have 180 divided by this beta what is so calculated. So, we will get a 9. So, total number of slots is equal to slots per pole into number of poles. So, we will have 9 into number of poles 12, which is equal to 108. So, now short pitch angle alpha is given as 1 time beta because short pitch angle alpha is calculated as the short pitch angle, and it is said that coils are short pitched by one slot. So, 1 into slot angle is equal to alpha. So, 1 into 20, so alpha is equal to 20 degree. So, Kp is calculated as cos of 20 by 2, that is cos of 10, which is equal to 0.9848. Winding factor has been asked to be calculated. So, winding factor Kw is equal to Kp, Kd what is already given. So, winding factor is equal to 0.9848 into 0.9598, which is equal to 0.9452. E phase, that is phase voltage of each phase, is equal to line voltage divided by root 3. It is calculated as 635.085, and when we substitute for E phase, Kw, F, T phase, we will get useful flux phi as 0.0168144 Webers. Total conductors are given as 180 into 3, because this is turns per phase, into number of phases you will get total number of turns, into 2 each turn constitute 2 conductor. So, we will get total conductors around the stator as 1080. Now, conductors per slot is equal to 1080 divided by total number of slots 108, which is equal to 10. Consider the numerical as a 3-phase 60 hertz. So, here you should note down the frequency is 60 hertz. In our country, standard frequency or nominal frequency is 50, and this 60 hertz is the nominal frequency in United States of America. So, 16 pole alternator has a star connected winding with 144 slots and 5 conductors per layer. See, in the earlier session we had discussed the winding can be arranged in one layer or 2 layers. So, here conductors per layer is given as 5, and it is said that the winding is double layer. That means, in one slot there are 2 layers, and in each layer there are 5 conductors. So, total conductors per slot is calculated as 5 into 2, that is equal to 10 conductors per slot. The flux per pole is 24.8 milliweber and is sinusoidally distributed. Find the speed, the phase EMF and line EMF. The coils are short corded by one slot. So, we will have speed N, that is given as 450. So, because it is 120 into F is given as 60, number of poles 16. So, N is slots per pole and it is given as 144 divided by 16, which is equal to 9. We will calculate beta as a 20 degree electrical, and M is slots per pole per phase. So, we will have slots per pole per phase as 144 divided by 16 into 3. So, we will get 3 slots. So, short pitch angle alpha is 1 time beta, because coils are short corded by one slot, which is equal to 1 into 20, and alpha is equal to 20. Kp is calculated as 0.9848 and Kd is calculated as M is equal to 3, beta is equal to 20, Kd is calculated as 0.9598. So, total number of conductors Z is given as 1440. So, that is number of slots 144 into number of conductors per layer 5 into number of layers 2. So, total number of conductors is 1440. Conductors per phase is calculated as 1440 divided by 3, which is equal to 480, and turns per phase is calculated as 480 by 2, which is equal to 240. So, when we substitute the various values Kp, Kd, frequency, flux, T phase, we will get phase voltage, its RMS value as 1498.739 volts. The line voltage EL is given as √3 times E phase, and it is calculated as 2595.892 volts. In the next numerical, we will see a 4 pole 3 phase 50 hertz star connected alternator has 60 stator slots with 4 conductors per slot. Coils are short pitched by 3 slots if the phase spread is 60 degree. So, here the new word phase spread is nothing but M into beta. So, phase spread is M into beta, which is equal to 60 degree. So, find the line voltage induced for a flux of 0.943 webers sinusoidally distributed in space. All the turns per phase are in series. Calculate the speed of the alternator. So, N we can calculate as 120 into F by P. So, we will get 1500. Slots per pole is 60 by 415. Phase spread, that is M beta 60. So, M is equal to 60 divided by 4 into 3. So, m is equal to 5. So, now slot angle beta is equal to 60, that is total phase spread, divided by 5. So, we will get 12 degree electrical. So, also beta is calculated as 180 by n. So, this is also possible. So, we will get same answers at 2 steps. Short pitch angle alpha we have calculated as 3 times beta, because coils are short pitched by 3 slots. So, we will get 36 degree, and Kp can be calculated as 0.9511. Kd, when you substitute m is equal to 5, beta is equal to 12. So, it can be calculated as 0.9567. Total number of conductors are calculated as Z is equal to 60 into 4, which is equal to 240, and T phase as usual can be calculated as 40. So, E phase, when you substitute all the values, and it can be calculated as 7619.5025, and multiplied by root 3, we will get a line voltage as 13,197.366. In the numerical what we are going to consider now, we have 4 pole 3 phase 50 hertz star connected alternator. Slots per pole per phase is 4 with 4 conductors per slot arranged in 2 layer. Coil span is 150 degree electrical. So, we know that if the coils are full pitch, coil span is equal to 180 degree. Since coil span is 150 degree here, it is the meaning that coil pitch is 150. So, that means coils are short pitched by 30 degree electrical. Find the no load line voltage induced EMF for a flux of 0.12 Weber, and also calculate the winding factor. So, m is given as 4, total number of slots given as 48, n is slots per pole calculated as 12, beta can be calculated as 180 by 12, that is 15 degree electrical, coil span is equal to 150 degree electrical, short pitch angle is 180 minus coil span, which is equal to 180 minus 150, that is 30 degree. Kp can be calculated as cos alpha by 2, and Kd can be calculated as sin m, that is 4, beta is 15. So, we will get 0.9577. Winding factor is Kp into Kd, we will get 0.9250. Z is equal to 48 into 4, that is 192. Z phase is equal to 64. Z phase by 2 will give us turns per phase 32, and we can calculate E phase as 788.58 by substituting the various data, and line voltage is calculated as root 3 times the phase voltage, that is 1365.861, and this is the last numerical we can calculate. So, here there are 8 poles, star connected alternator, 750 RPM, flux per pole is 50 milliweber, stator slot 72, conductors per slot is 10. Calculate the percentage rise in open circuit terminal voltage if the windings were concentrated and accommodated in 24 slot with the increased depth to house 30 conductors per slot. So, in first case with 72 slots, the calculations are as usual. So, we will calculate Kp as equal to 1, Kd as this 0.9598, winding factors, Z, the procedural step remains the same. So, we get E phase is equal to 1278, line voltage as 2214.34. So, now in the second case it is 24 slots and number of turns per slot is now 30 instead of 10 earlier. So, we will get here Kp is equal to 1, Kd is equal to 1, winding factor is equal to 1, total Z remains the same because 72 into 10, now it is 24 into 30. So, 720, T phase remains the same and we will get E phase 1332 and line voltage as 2307.0 0.09. So, percentage increase in terminal voltage we will get with concentrated winding 2307 with the distributed winding 2214 divided by, or this difference expressed as the percentage of 2214 into 100. So, we will get 4.19. That means, with the concentrated winding we will have 4.19% increase in the induced EMF. So, we will look at a video, short video, which will tell us the working principle of hydroelectric power plant. In this power plant, production of electricity depends upon water level from the ground, volume of the water, that is total water available in the dam, and then the efficiency of the turbine. So, water is stored in water reservoir, and we will have the dam to hold the water in the reservoir, and you can see here the construction of dam, and we will take the stored water through this pipe which is called as penstock. So, water is allowed to flow through this penstock, and water is allowed to impinge on the turbine blades, and the penstocks can be made up of concrete or steel, and you can see here water is coming in, and there is a surge tank. In case there are blocks in the penstock or the inlet control valve is suddenly closed, then there is a pressure built up in this surge tank, and this pressure is taken up by surge, and if there are any debris, then this trash rack is going to prevent debris entering into turbine and causing the harm to the blades. So, now water flowing and impinging on the turbine is causing to rotate this shaft, where the shaft is coupled with the generator rotor, and generator rotor is going to rotate, and this is the alternator which produces electrical energy, which converts mechanical energy to electrical energy, and converted electrical energy is transmitted over transmission lines. And whatever the water coming out of the turbine is collected in the draft tube, and it is flown out. And since the demand of electricity varies by day and night as well as among the seasons, there is a need to store the energy so that it can be used at a time of high electricity demand. So, in such cases we have pumped storage process, where the water in the tail race is pumped back to the dam. To conclude, we have at the end of third session, audience will be able to explain the working of three-phase alternators, predict the behavior of alternators, select the type of alternator required for a particular application, apply the knowledge of mathematics in solving numerical problems. I would like to acknowledge VTU Belgaum, Nette Education Trust, NMAM Institute of Technology, and the faculty members of Department of END NMAM IT, in particular Mr. Ravi Kiran Rao and Mrs. Swati Hatwar have completed the presentation material and supported me at times. Thank you.